Hey everyone, we're going to make a video on metric and Cauchy spaces, just defining what they are, maybe giving you some justification for why they're two different things. So let's take a look. So a metric space is a set X along with a function D from X Cartesian product with itself to the real numbers, subject to the following constraints. For any three elements of X, the distance between two of them is greater than or equal to 0, so this is a non-negative function. If the distance equals 0, x equals y, the distance between 2 points is 0 only when they're the same point. It's symmetric, so it doesn't matter which point you list first, so distance xy is equal to distance yx. And the triangle inequality. If you make a stop going from x to y, it takes longer or the same to get there. So that's a metric space. It gives you a distance, but not really a direction, so to speak. You know that if you go from here to here and stop somewhere in the middle, it'll take you longer to make the two legs of the triangle than just one. But we don't really know too much about distance, or direction, I mean, in metric spaces. We just know how far apart things are. So that's going to be what we have. We have a very good generalization of distance, a lot more refined than a topological space. You can define any metric space to be a topological space just by defining open sets in the natural way. We'll get into what that means at some point if there's interest. But what's a Cauchy space? Well, a Cauchy space is just a complete metric space. What that means is Cauchy sequences are convergent. A convergent sequence is a sequence such that there exists a limit for every epsilon greater than 0. There exists a natural number in n. So the natural number does not depend on epsilon, depends on epsilon, but epsilon does not depend on your choice of limit. Your limit has to be a certain number. You can prove that it's unique. So the order of those quantifiers does matter. So you have this natural number n. That means if you pick an index j bigger than or equal to n, that's going to imply that the distance between x sub j and x is less than epsilon. In other words, the tail stays near the limit, arbitrarily near the limit, as a matter of fact. Let's look at the other side of things. A Cauchy sequence is, for every epsilon greater than 0, notice we don't have a limit, there exists a natural number n. Two indices bigger than n implies that the distance between those two is less than epsilon. So as I explained in the video where I proved this, that Cauchy sequences are convergent, which by the way is our next fact, Cauchy sequences, or convergent sequences are always Cauchy. The difference between these two is a convergent sequence is a Cauchy sequence where you nail down the epsilon ball, whereas in a Cauchy sequence, your epsilon ball that the tail has to stay in is allowed to kind of wiggle around. So you can prove that any convergent sequence is Cauchy, but it's not always the case that a Cauchy sequence is convergent. You may be familiar with the fact that some sequences of rational numbers converge to irrational numbers. Well, you could take your metric space to be the rational numbers, and then you have a Cauchy sequence in the rational numbers that converge outside of the rational numbers. So what you have is the Cauchy space associated with the rational numbers is in fact the real numbers. That's just to give you an idea of the fact that this is non-trivial, that they're different. Anyway, go ahead and like, comment, subscribe. Let me know if there's any questions, and I'll see you in the next video.